Hello. Today we're going to be talking about functions as relations. So we're going to go over some basic ideas of what a function is and some basic theorems and properties. So let's begin. So starting with definition 1, a function or mapping from the sets x to y is a relation f from x to y such that 1, the domain of f is the set x, and 2, if the ordered pair xy is in F and the ordered pair xg is in F, then y must be equal to g. So we usually write F maps x to y, so it's red F maps x to y, and we call the set y the domain. And note that that's not necessarily the range of F. So this picture here kind of illustrates the idea that here we have our domain, set x, being our domain. So this is our domain. This, f of x, is our range, and y is our codomain. So not every element in the set y has to be mapped to an element in the domain. So, however, each element in the domain is all mapped to a unique element in the range. So that's what condition 2 states, is that y and g can't be unique. They have to be equivalent. Another way to define the range of f is mathematically, is if we have an element y in the codomain such that there exists an element x in our domain such that xy is an f. So the element y is in the range of f if there exists an element x in our domain such that xy is an f. In other words, there has to be an element in the domain that maps to an element in the codomain. Okay, so let's move on from that, and let's look at the first consequence of that, which is Theorem 1. So Theorem 1 states, two functions f and g are equivalent if and only if, 1, the domain of f is equal to the domain of g, and 2, for all x in the domain of f of x equals g of x. So to prove this, it's a biconditional. So we have to prove the forward implication and the backwards implication. I'm going to prove the forwards implication. The backwards implication is fairly obvious. So I'm going to first just prove the forward implication. So I'm going to prove consequence 1, which is the domain of f equals the domain of g. So I want you to keep in mind that the domain of f and the domain of g are sets. So how do we show two sets are equivalent? Well, we must show, so we have to show that the domain of f is a subset of the domain of g, and the domain of g is a subset of the domain of f. So if we show those two conditions are true, then that implies that the two sets are equivalent. So the first thing I'm going to say is let x be in the domain of f. So I'm starting with an element x in our domain of f. So since f equals g, so our assumption for the forward implication is that f and g are equivalent, and we have to show that these two conditions hold. Since f equals g, we have xy and g as well, right? For some y. Therefore, this implies X is in the domain of G. And we conclude that the domain of F is a subset of the domain of G. So first we started with X in the domain of F. We concluded X is in the domain of G. So from there we assume the domain of F is a subset of the domain of G. So to show the other way around, I'm going to start with the an element X in the domain of G, and it's going to proceed in basically the same way. So I'm going to say let X be in the domain of G. So since F equals G, we have X, Y in F for some Y. So therefore, this implies X is in the domain of F. And that shows the domain of G is a subset of the domain of F. So since we showed that the domain of F is a subset of the domain of G, and the domain of G is a subset of the domain of F, we're done. So that's consequence 1. So let's prove consequence 2, which is for all X in domain of F, F of X is equal to G of X. So this one is actually pretty straightforward. So I'm going to first say let X be in the domain of F. So then for some Y, we have xy in F. And that's true because F is a function. And then also, since F equals G, we have xy in G. So therefore, F of X must be equal to G of X. So that's pretty straightforward. Not much to say there. So that proves theorem 1. So let's continue. Now definition 2 is a little more hefty. Here we're defining the inverse functions of F and the composition functions. So definition 2 states let the functions f and g be such that f maps a to b and g maps x to y. The inverse of f is defined to be the relation from b to a such that the inverse of the function f is equal to xy, ordered pair xy, such that the ordered pair yx is an f. And then the composition of f and g is the relation from a to y, such that g compose f is equal to xz, such that there exists in y and b such that our ordered pair xy is an f and our ordered pair of y is an g. So to understand the basic idea of this, what we're essentially doing for the inverse function is we're mapping b to a. So if I have elements in the set A, 3 elements in the set B, I'm essentially mapping it the other way around. And then for the composite function, I'm essentially mapping A to C, which we'll prove in the next theorem. But essentially the basic idea is we're going from A, we're skipping B, and then we're going to C. So one thing to note is that each element of the domain of a function has a unique range. So what we could do is simplify the notation for the composition of a function, because here they're saying, okay, so we have, let's say, an x, y, and f, and we have a y, z, and g. Well, what that means is that we have y equals f of x, and z is equal to g of y. So what we could write is instead is that f compose g, I'm sorry, g compose f is equal to g compose f of x. It's a function, but we're going to prove that it's a function in the next theorem, actually. And that's equal to g of f of x. So these are alternative notations you can use for the composition of functions. But let's move on. Theorem 2 states, and this is where we're going to prove that g compose f is a function. So let a, b, and c be sets. Also let the function f be such that a maps to b, and the function g be such that b maps to c. Then g compose f is a function from a to c, with the domain being the set A. So we need to prove two things. So we need to prove that g compose f is a function, and we need to prove that the domain of g compose f equals A. So I'm going to start with the first consequence. So I'm going to say, so let x, y be in g compose f. So what I'm going to do is I'm going to say, okay, I'm going to say there's an ordered pair x, y, and g compose f, and I'm going to say there's an ordered pair x, z, and g compose f. I want to show that y is equal to z. Well, if we look back at definition 1, one of the conditions of a function is that if you have x, y, and f, x, g, and f, then y must be equal to g. So what we want to show here is that y is equal to z. So I'm going to say, okay, by our definition of a composition of functions, so by definition 2, there exists an element u in B such that x, u is in F, and u, y is in G. So similarly, I'm going to pick another element. There exists a V such that x u is, I'm sorry, xv. Just erase that. So xv is in F, and vz is in G. So since F is a function, we can assume that's a function to the theorem. And xu and xv are in F. We know u equals v. So since F is a function, u must be equal to v by definition. Similarly, I'm going to say also, because g is a function, uy and vz are in G as well. So really what this simplifies to is uy and uz are in G. Since u equals v. So what we're going to conclude is that so y must be equal to z. So since y equals z, G compose F must be a function. So that proves the first consequence. So now let's prove the second consequence. So I'm going to use a blank page up here to prove the second consequence. So second consequence, we need to show that the domain of G compose F is equal to A. So what I'm going to say first is let little element A be in capital A. So since A is the domain of F, there is a little b in capital B, such that the ordered pair AB is an F. Also, since B is equal to the domain of G, there is a little c in capital C, such that ordered pair BC is in G. So by our definition of composition of functions, so by definition, AC is in G. So thus, domain of G compose F is today. So since A is the domain or an element in the domain of G compose F, I should write G compose F there. we have to assume that the domain of G compose F is A. Okay, so that shows the second consequence. So let's move on. So now we're on Theorem 3, which states that we're letting A, B, C, and D be sets. And we're also letting the functions f map A to B, function G map B to C, and the function H map C to D. So we want to show that H compose G compose F is equal to H compose G compose F. So one thing I want you to note is what we just proved in Theorem 2 is by Theorem 2, H compose G compose F is a function with domain A. So what we just showed was that a composite function is a function, and we also showed that the domain in this case of our composite function would be A. So what we could say is let X be an A, then H compose G compose F of X. So we're evaluating this function at X. This is equal to H compose G of F of X. So remember the alternative notations for the composition of functions. So G compose F of X is equal to G of F of X. That's what I'm doing here. Now, again, we can rewrite this as H of G of F of X, which is equal to H of G compose F of X which again, using the same, alternative notations, is H compose G compose F of X. So by Theorem 1, this implies that they're equivalent. Let me rewrite that. So H compose G compose F is equal to H compose G compose F. So we asserted that, H compose G compose F has a domain A. So what we concluded is that H compose G compose F would also have domain A, and their evaluation at the point X would be the same. So by Theorem 1, the two functions have to be equal. So that proves Theorem 3. That was a pretty short one. We could have a little pictorial here just kind of showing what's going on here. So if I were to draw these sets out, let's see, A mapping to B is defined to be F in the theorem. B mapping to D is H compose G. C mapping to D is H. So they said C to D was H, A to B was F, B to C was G, so B to D would be H compose G. So we start with the domain B, and then we map to the range of H, which is D. And then A to D would be H compose G compose F. So that's kind of how the mappings are working. So that proves Theorem 3, so let's move on. So Theorem 4 is pretty short. So we're saying let F be a function such that A maps to B, I sub A be a function such that A maps to A itself, and I sub B be a function such that B maps to B. We want to show that the composite functions of F and I sub A is F, and the composite function of I sub B and F is F as well. So the way we could think about I sub A is if you're mapping something to itself, you're really saying I sub A of X equals X. Or a more common way of writing it is Y equals X. That's another way of thinking about it. So that is what that's saying. We could draw it out too. So if I have the sets A and B, I know from the mapping from A to B is defined to be F. The mapping of A to A is just a mapping of itself. So I could draw like a little loop to show the mapping of itself, and I'll write I sub A. And then B, the same thing. The mapping from B to B is I sub B. So what I want to show is that when I take the composition of these functions, I end up just getting the function itself. So by inspection, the domain of F compose I sub A is equal to the domain of I sub A, right? The F and I sub A both share the same domain. And then that would also be equal to the domain of F, which is equal to A. So if X is in A, then F compose I sub A of X, so the evaluation, the composition of the function at X, is equal to F of I sub A of X. But what did I write up here? Well, I said, okay, well, the I sub A evaluated itself, or at X, is itself X. So that would be equal to F of X. So therefore, by Theorem 1, F compose I sub A is equal to F. So they both have the same domain, and they both have the same evaluation points in the range. So the functions are defined to be equivalent by Theorem 1. So now we're going to show that I sub B compose F is equal to F now. So it's done in a very similar way. So I'm going to say, okay, by inspection, the domain of I sub B compose F, compose F, is equal to the domain of F, which is equal to A. So here I'm deducing that it's equal to A by the definition, or by the theorem we just proved, saying here that if you have G compose F, the function maps A to C with the domain being set A. So that's a similar argument here. I'm just using that theorem to assume that the domain of I sub B compose F is A. So now I'm going to say, okay, let X be in A. So then the composition evaluated at X is equal to I sub B of F of X. Now, what we have here is really F of X. So what that would equal is just F of X itself. Right? So therefore, by theorem 1, the composite is equal to F. So what I'm saying here is that we have the identity function B, which essentially maps all the elements in B to B. So you could say all the elements map F of X to F of X. So F, the identity function of F of X is equal to F of X. So I don't think I should be saying this necessarily, but what we're saying here with the identity function B is that we're mapping all the elements in the set B to itself B. So if I pick an element in B, which F of X is an element in B, the identity function would output the same thing, F of X. So therefore, by theorem 1, we showed that the domain is A. We showed they were equivalent, or the domain of F, the domain of I sub B compose F, and we showed that the evaluations are the same. So therefore, by theorem 1, the composition has to be equal to F. Okay. So move on to the last theorem, which is theorem 5. Theorem 5 states, let F be a function such that A maps to B, and I sub A be a function such that A maps to A, and a function in I sub B be a function such that C maps to C, with the range of F being equal to C. So if the inverse function is a function, then the composition of the inverse function and the function itself is equal to I sub A, and the F compose inverse of F is equal to I sub C. So I'm going to show the inverse function compose F is equal to I sub A. The other way around is very similar, so I'm just going to prove the this consequence here. So I'm going to say, okay, let F be such that A maps to B, and the inverse of F be a function. Because if it's not a function, then we can't really prove this there. Then the domain of F inverse compose F is equal to the domain of F by theorem 2. Thus, the domain of the inverse of F compose F equals the domain of F, which is equal to the domain of I sub A, which is equal to A. So since the ordered pair x f of x is in F, this implies f of x is in the inverse of f. That's just by definition of the inverse function. So therefore, by definition, again, by definition, the composition F inverse compose F would have x in the function. So you would have a function that essentially maps itself. Let me real quick rewrite that. I like writing it that way. So we're basically combining the definitions of the inverse function and the composition of a function. So let's go up real quick. So we said, okay, if x, y is in F, yx would be in the inverse of F. And then if we take the composition, what we would end up getting is just a pair xx. From this, we conclude that the inverse of f, compose f, evaluated at x, is equal to x, which is also equal to the I sub a of x. So therefore, inverse of f compose f is equal to I sub a. And that shows, that's our statement there. Like I said, f compose inverse of f is done in a very similar way. So thank you for watching. Have a good day.